Welcome everyone. I begin with paying my respect to First Nation custodians of country throughout New South Wales, in particular, Gadigal people of Eora Nation, the traditional owners of the land on which the University of Sydney is built. I pay my respect to their elders past, present, and emerging. Welcome to another Sydney Nano Distinguished Lecture on the world of liquid metals, liquid-based electronics and optics. It is my absolute pleasure to introduce our distinguished lecturer, Professor Kourosh Kalantar-Zadeh, a professor of chemical engineering from the University of New South Wales. Professor Kalantar-Zadeh has a long list of achievements, awards, and recognitions. Just for the sake of time, I just limited to mention that Professor Kalantar-Zadeh is an ARC Laureate Fellow. In a great recognition recently, he's awarded the Robert Boyle Prize by the Royal Society of Chemistry for outstanding contribution to analytical sciences. With more than 32,000 citations, he is one of the highly cited researchers in Australia and around the world. He's internationally recognized for his work on sensors, two-dimensional semiconductors, and liquid metals. He's a member of the editorial board of many prestigious journals, such as Applied Materials Today, ACS Sensors, ACS Applied Nano, and ACS Nano. With that, I will hand over the microphone to Professor Kalantar-Zadeh. We have his presentations, and then we have the Q&A after that. So I just hand over to you, Kourosh, with a virtual clap, basically.
Thank you very much. Thank you very much, Amit, for this nice introduction to the talk. So I would like to thank Sydney Nano for inviting me for this forum. And actually, so far till today, I rejected anything online. It's my first time I accepted, just because I know Amit from a long time, and I thought I should come back on presentations. So here is my first presentation since March. So what I'm going to present here doesn't belong to me, but the group. They spend their time. I mentioned a few of the names here, and of course there are many more. Funded by Fleet, funded by ARC Laureate Fellowship, and of course both UNSW and in the past RMIT University that I worked at this university before moving to UNSW. Okay, so today I'm going to talk about liquid metals. What are they? These are the famous ones are mercury, francium, cesium, gallium, and rubidium that take the liquid state at near very, very close to room temperature. They are fluid, they are flexible, they have high thermal and electrical conductivities, high entropy, and they can also mix and alloy with many other metals. More importantly, that I didn't write here, is that they have free electrons, and ions can move freely around this liquid as well, but free electrons are very important because they're metals. Only mercury and gallium are suitable for practical applications because francium is radioactive, cesium and rubidium are explosive. Talk about mercury. Anytime I would like to talk about mercury, everybody raise their eyebrows as talking about the hazards of mercury. I don't believe that's that hazardous, but that's another conversation. What remains as talking freely and safely about is gallium. Establishing a whole field based on just one metal is very limiting. So what I did together with my colleagues, I cheated and I put gallium, indium, tin, lead, bismuth, and a few other members around this liquid metal, post-transition metal category into this liquid metal family. And I define it anything that melts below 330 degrees. And it makes sense because the kind of temperature that we have access at kind of basic kitchen at home. So basically you can melt everything you want at this kind of temperatures and play with them and experience with them. Now, back to the representative of this group, gallium. Melting point is 29.8 degrees. That means it's solid at normal room temperature. You put it at the palm of your hand. Your 37-degree temperature, body temperature melts it. It can alloy different metals at very high concentrations like indium, tin, bismuth, and zinc at more than 2-3%. They make very interesting alloys. Some of them are eutectic alloys. Eutectic is the definition of the alloy that provides the lowest temperature because it has the highest entropy of the combination of those two. For instance, E-gain, 75% gallium and 25% indium. That decreases temperature, melting point temperature to 15.7. Or gallium bring the temperature even lower and has more tin in it, 10% tin. And actually, both of them also offer supercooling properties. Again, it's another topic for another talk. Now, what is very important about gallium, tin, others, is that these elements, these metals, at ambient oxygen produce a layer of oxide around them. For some of them, like gallium, is self-limiting. That means the layer goes to 1 or 2 nanometers. It doesn't go further than that at 21%. Although for tin and bismuth, it grows and grows and becomes thicker. Now, what does it mean to have this layer? Look at the figure. This is from my colleague and friend, Michael Dickey, at the University of North Carolina. They were managed to print small droplets of gallium on the top of each other. The 2-dimensional layer around it encapsulate them and hold them together and give them integrity for this printing. Basically, we can go from Newtonian rheological characteristic to non-Newtonian. That means like mercury that doesn't have this layer, everything becomes spherical droplet, then energy is not applied. Here, because of that 2-dimensional layer, very similar to any 2-dimensional layer like graphene, molybdenum disulfide, it holds the structure together. Can we see and observe this 2-dimensional layer? Yes. Just take one of these liquid metal droplets, shake it, it breaks down, and it detaches itself from the surface. It goes and restack on the top of each other, makes these multi-layer structures. Regardless, if you look at this figure H, you can see how it wrinkles on the surface of liquid metals, and you can observe it. Now, I present a few things in this concept. Talk about non-crystalline nanoparticles in liquid form, crystallization when they transform into solid form, heterostructuring, how we have this structure of 2-dimensional material on the surface and use them, and phase separation when we cool them down, what's solid and how they're formed from the liquid metals. Again, we can talk about many more. For today, I limit myself to these 4 topics and give you some of the examples. Liquid metal. You can sonicate a liquid metal and break them down into smaller particles. As you see, you have a 2-dimensional layer around it. They encapsulate them. It makes them stable. It makes them small particles. For instance, you see submicron or nanoparticles on top of each other. When you increase the sonication time of this liquid metal in the secondary solvent, and you can make films of high surface to volume ratio while these films are made of liquid metals. So you can make very interesting sensors, electronic devices. Here, we introduced a sensor that with voltammetry, you can swallow, for instance, lead and cadmium into this liquid metal and spit them out, and then measure the current. And current measurement give you the intensity, the concentration of the heavy metal ion in the environment is proportional to this current. Basically, it's a heavy metal detector. Actually, it has been commercialized. This is a paper from 6-7 years ago, and now it has been deployed to many water reserves around the world. Very highly sensitive. So you can actually make very safe systems out of just simple sonication of this material gallium. In comparison to, as I mentioned, to mercury, gallium is very safe. You can deploy it everywhere you want. Heterostructuring. You heard about two-dimensional materials. The fever about these two-dimensional materials came from graphene, Gaim and Novoselov. Years and years ago, 2010, they received the Nobel Prize, and 15 years ago, they introduced these materials to the world. Now, it's always about, okay, when can we deposit these materials on the surface? Vapor scale. When can we bring them into commercialization? So I was actually one of the first people. I was the first group. My group was the first group that defined the chemical vapor deposition of transition metal dichalcogenide for the first time, MOS2. And now you can buy the commercial version of these reactors that it can deposit two-dimensional material of molybdenum disulfide, tungsten disulfide, which are semiconductor version of these two-dimensional materials on the surface. The problem is we need nucleation happening on the surface, and everything grows from that central nucleus. For instance, for molybdenum disulfide, as you see here, there are very large triangles that eventually they are separate triangles. They grow. If you highly control it, they stitch together. They don't grow on the top of each other, but they really grow on the top of each other most of the time. The growth is very small rate. If you use other methods, and as you see, it doesn't even cover the surface fully. You use other methods that cover the surface, and it's two-dimensional, like MBE, molecular beam epitaxy, is very expensive. You need super high vacuum. All these problems, they haven't been commercialized yet. I mean, the wafer scale solution, not the reactors. Going back to what we can obtain from liquid metals is that natural two-dimensional oxide that appears on the surface, or if you change the environment from oxide to sulfide, natural metal sulfide compound that have very interesting semiconducting property. If we resort to low melting point materials, like gallium, indium, bismuth, tin, we can melt them, let them oxidize, let this oxide to form on the surface, and then harvest them. Oxidation happens under the scheme of Mott-Cabrera definition. What does it mean? That we don't need nucleation. Oxidation on the surface happen at the same time. We get a single perfect crystal on the surface. So you can imagine, you make the area, the bulk of liquid metal very large, and you can harvest it. How do you harvest it? You bring a substrate near the surface. You just touch the surface of liquid metal and two-dimensional material on the surface of that liquid metal. The substrate, and it transfers itself, exfoliates itself onto the substrate, because substrate has very weak van der Waals forces, while liquid core is just liquid. It's non-polarized. It doesn't have any force. So transfer is very easy. Here is an example. Even with a piece of glass rod, from a surface of a tin, melted oxide can be, the oxide on the melt can be removed. Now, tin is not self-limiting. This is why we can see the oxide so easily with naked eyes, because these oxides become thicker and thicker. Becomes thicker, become yellow, thicker than that, red oxide, 15 minutes, then half an hour, you see gray oxide. You see all these beautiful colors on the surface of tin or bismuth. Although if you reduce the ambient oxygen from 21% to less, it becomes self-limiting as well. Now, can we repeat the exfoliation and put it on different substrate? Yes, as you see, scaling up commercialization is very easy. Reduce the ambient oxygen, for instance, for tin oxide, tin monoxide, to a few, do it in a cloud box with control oxygen, bring the substrate to the surface, do it again and again and again, and you can harvest tin oxide as many times as you want. Can we pattern them for optical electronic purposes? Yes, it's very easy. For instance, you can put the oxide on the surface and pattern them, or do the opposite. Here, an example of the reverse. We put the photoresist, we expose it to light via pattern, and we did the lithography. We removed the photoresist from the areas that we didn't pattern. We cover those areas with a fluorinated material to make the surface hydrophobic. What does it mean? Hydrophobic means liquid metal doesn't stick to those areas, but the oxide of liquid metal sticks to the areas where it's bare. So we put a liquid metal droplet on the surface, oxide of the liquid metal attaches to those areas. We take a squeegee and we clean the liquid metal from the surface. What remains on the surface, as you see, is the oxide pattern. Oxide of gallium is very useful. We can make transistors for power electronics, or you can then go back to more conventional electronics, produce gallium, for instance, sulfide. This example, within a two-step process, we expose it to hydrogen sulfide, and then we expose it to hydrogen chloride, produce gallium chloride, and expose it to sulfurs. We did the sulfurization at under 300 degrees, very low temperature, to produce gallium sulfide. Photoluminescence show it's very homogeneous, and it's made of 2 layers of gallium sulfide because the unit cell of gallium sulfide is 2-layer. That's how the most stable structure, 2-dimensional, comes out. We made a transistor, we made photo transistors that I'm not presenting here. You can do further work. For instance, here we deposit 2-dimensional gallium nitride. Gallium nitride is a very famous material. If you look up and if you have these energy saving lights that they have LED in them, they're made of gallium nitride mostly. They're wide band gap semiconductors. Their mobility is very high, and the base material is gallium. So we did the same thing. We made the gallium on the gallium oxide on the surface, harvested it, and then we use a precursor of nitrogen at 800 degrees for 90 minutes. We transform it to gallium nitride. Wide band gap 3.5 electron volts, and mobility was actually very high, 20 cm square per volt second. Actually, it's a good quality material to make the blue LEDs from it. Another thing that we did, can we make 2-dimensional piezoelectric materials? You can actually use this, put it on silicon substrate, take it to cars as accelerator detector. So when you have accident, it allows the release of the what's called the protection airbags, the protective airbags. So here we put gallium oxide on the surface, and we use hydrogen phosphate. We evaporated hydrogen phosphate at 350 degrees. It transformed gallium oxide to gallium phosphate. Is a piezoelectric, wide band gap piezoelectric material. The piezoelectric coupling coefficient is out of plane, is very high, 7.5 picometer per volt. It's actually double that of the bulk. So very easy to make, low temperature, and you can actually take it and commercialize it right now on silicon substrates. Other thing that now we are negotiating with the company to commercialize it is to print ITO glass. ITO, if you look at your mobile phones in front of you right now, or your displays that you're looking at me using them, many of them, they have ITO, they're transparent. Oxide, ITO, the famous one, indium tin oxide, made of indium and tin, the 2 famous post-transition metals. If you mix them together, the temperature, melting point temperature goes down. You just put everything on a droplet like this. We squeeze printed them. As you squeeze 2 substrates together, liquid goes out. What remains is the oxide. Transparent, very transparent, 1 layer, 2 layers. The oxide is made of separate grains stitched together, and we can go 1 layer, 2 layers, or more by double printing, triple printing. Interestingly, we combine tin and indium together. The ratio that comes to the surface, the enrichment, is double that when, of tin that we mix them together. For instance, you put 5% tin inside, what you get on the surface is about 10% on the surface. And you harvest it. When we harvest only one layer, the conductivity wasn't that good. When we made 2 layers, the conductivity became very comparable with commercial ITO glasses that you buy. Now, what's the advantage? It's a 2-dimensional material. It's flat. It's like a piece of paper. You can put many pieces of paper on the top of each other. You can easily bend them. But if these papers are made of grains, when you bend them, they break. So basically, there is no commercial ITO or any other bendable conductive material that can last forever when you bend them. Here, you can bend them forever. As you see, you have bent them 3,000 times, actually almost folded them, and it still didn't work. Another advantage is that they are super transparent. The absorption of ITO glass is more than 5–6%. Here, absorption is almost only 1% at 2 layers with a very similar conductivity. So very soon, I think, and another thing that I didn't put in this slide is that it's a new crystal of ITO. So basically 3 discoveries in one paper. And very likely it will change the concepts that we have about transparent conductive oxide of the future. Now, everything was about post-transition metals. Can we expand the same concept to transition metals, lanthanides? Is it possible to obtain 2-dimension of those materials using this liquid metal process? And are we able to extract more 2-dimensional materials, new crystals that we are not familiar with? So I had this idea. I told my students, his name was Ali, hey, go and try other metals, dissolve them at low concentration and see whether they come to the surface or not. Actually, it was an idea that me and my colleague Torvind and Eke, we had, that the surface of material seems to be, there is a competition between different metals that come to the surface. So this Ali went and tried different metals and came back with the outcomes that, yeah, oxide of gadolinium, aluminium, hafnium, and many other oxides come to the surface in competition to gallium oxide. Although indium oxide, tin oxide, copper oxide, silver oxide, they don't win the competition. So we look around, and this Torvind had an idea when look at some of these numbers, realized that Gibbs free energy of gallium oxide sort of can be the reason that if the oxide of this material that come to the surface they have lower Gibbs free energy, they win the competition, not other oxide. Now, what are the technological consequences? Hafnium oxide is actually the famous one. Hafnium oxide is the oxide of use, of desired, for making field effect transistors that you find in all your mobile phones. But those oxides which are used in mobile phones came from, for instance, chemical vapor deposition or other methods of deposition. The thickness is 3–4 nanometers. They make it thinner, it becomes full of pinholes. Hafnium oxide, which is produced here, is much thinner, 0.6 nanometers, 0.5 nanometers, and it's pinhole free. So you can use it as dielectric instead of applying a voltage of 1 or 2 volts to turning on your transistor, because thinner, you can go to lower voltages. So again, many companies are looking at this hafnium oxide to change the technologies and make them better for a transistor and make them lower consumption. Now, aluminium oxide can be made also in small flakes, large scale flakes. Can be used for different applications. Here is an example. For instance, you put aluminium, you alloy aluminium into gallium, and if you expose everything to vapor of water, you produce rods coming out because of nucleation on the surface. We don't want to use them. If you put everything underwater, the layer of aluminium oxide, aluminium hydroxide are formed on the surface. Hydrogen is formed at the same time. Hydrogen push this layer out of the surface, delaminate them. The corners of this delaminations, they stick to each other and they make this beautiful hydrogel, like a filter, a few nanometer distance between the planes of bohemite, which is aluminum hydroxide, or you can basically anneal them and produce aluminum oxide and make these filters. The filters for heavy metal ion, because aluminum oxide is known to absorb heavy metal ions like lead at very, very high concentrations. And also the distance between the planes is very small, so anything else like oil can be trapped between them. And we go from dirty water to very clean water very quickly. The flow rate is very high. Now, can we do other things? I said if we change the ambient, we can go from oxide to sulfide. Here, in sulfide, structure like this, as you see, it's like accordion. We can stretch it forever. As a result, the calculation shows that the predicted value of piezoelectric coupling coefficient for this material is very high, 144 picometer per volt. Actually, it means that if you have a layer of this tin sulfide and you just bend it, it should produce about 2 volts voltage for you. That will be an extraordinary, and of course, it's a semiconductor with a small band gap. If you make the contacts properly, you can harvest current. A large voltage, a large current. That means just by bending, you can produce power. Okay, going back how to produce it, we change the ambient from oxygen to hydrogen sulfide in a glove box, and we harvested the surface layer, tin oxide, no, tin sulfide this time. And you cannot do this as any other method. You know, the prediction came about 2015. Why only liquid metal worked? Because we have also, in addition to van der Waals forces between layers of this layered tin sulfide structure, there are interlayer interaction as well because of the lone pair electron of S. Hold them together so nobody can exfoliate it mechanically. This is why we were the first time successful in making this tin sulfides. The layer is fantastic, single crystalline. You could transfer it to any substrate. One layer, and as I mentioned, single crystalline. You see the example of looking at one layer that we harvested from the surface and put it on a TM grid, and we look at the crystal, is all the same orientation. The band gap is 1.4. It's one of the only materials that when you go from bulk to single layer doesn't open the band gap. The mobility is really high, 35 cm square volt per volt second, and it's p-type. That's very important. We don't have many p-type material of these properties. And we did the energy harvesters, and we could obtain about 200 millivolts voltage. And the result of the piezoelectric coupling coefficient was 30, about 7 times less than prediction, 6 times less than prediction, but still it's a record for the voltage, output voltage, and also output power that we obtain out of this system. Now, we talked about dissolving things into liquid metals. What if the material cannot be dissolved? Manganese. Well, we cannot alloy manganese into liquid metals, but we can still use the properties of surface properties of liquid metal to obtain two-dimensional materials. Here is an example. If we have permanganate potassium on the surface, the ions come near the surface and produce manganese oxide, two-dimensional materials which are self-limiting. Gradually exfoliate themselves from the surface, and you can have this fluffy two-dimensional material growing on the top of each other, stacking on top of each other of manganese oxide out. Very interesting observation. We thought, okay, these things are possible. How about the most famous material, like two-dimensional carbonaceous material, graphene or graphene oxide? Can we break down organic precursor on the surface with a little bit of energy? We did the DFT calculation. It shows that, yeah, it's possible. Bring some organic material. Here we try methanol, ethanol, isopropanol, glycerol, And the list here, as you see, rings to just small molecules and also molecules that have nitrogen in them near the surface to see how they break it on the surface. And DFT calculations show that they do. We use an electrochemical cell, 3 of them, as I'm showing to you here. Just put a reference electrode against, apply a voltage between the liquid metal. We fill environment, precursor, organic fuel, and we apply the voltage. Here's what's happening when we don't have the fuel and this liquid metal. We apply the voltage, it deforms in time, nothing happens. Now, here, when we have the organic fuel, you see the surface color changes and you get this graphitic material on the surface. Okay, it seems that it works. The characterization. Raman shows, hey, it's not the perfect graphitic material that we wanted. It looks like a amorphous graphene. And when we look at it under TM, we realize, oh, it's very porous graphene oxide, highly porous, as you see, nanopores. Reaction happened best when we had 2 elements added to the liquid metal. Gallium by itself really wasn't that great. E-gain, which is indium and gallium, wasn't that great, as you see, even the current is small. Gallium, when we had indium and tin and gallium, worked best. Now, we wanted to obtain the kind of 2-dimensional materials without pores as well. Of course, those porous materials are fantastic materials for making battery electrodes. What if our intention is to make 2-dimensional graphene without any holes? So what we did, we changed the setup. Instead of having a liquid metal that can deform and gradually during the formation make the pores because the 2-dimensional materials which are formed on the surface, they break quickly. Here, we hold it on a copper substrate. We just painted the liquid metal on this electrode, and we put another secondary electrode in parallel with it, and we apply the voltage. Actually, they self-exfoliate because of the voltage go to the other side. The surface is not porous anymore. It's become highly crystalline. Actually, we realized when we use glycerol or when we use ethanol, we could get very highly crystalline graphitic material. Sorry, when we use pyridine and when we use ethanol, we could get very highly graphitic, highly ordered material. Ethanol was very interesting because we could get graphene oxide. All the signatures of graphene oxide were there. But pyridine has nitrogen in it, this organic fuel. We could get the nitrogen doped graphitic material. As you know, these materials are very fantastic catalytic compounds. And we did everything at room temperature. Actually, it was the first time a graphitic material could be obtained at room temperature. I think technologically it's a very important demonstration. Now, crystallization. Let's leave the 2-dimensional material at least as they are, and combine them with something else, another observation. So many of these materials, like lanthanum, like many of the transition metals, they don't really dissolve at high concentration in liquid metal gallium or other post-transition metals. For instance, the solubility of cerium is only 0.1% in gallium. So what will happen? What happens if we dissolve more of this material? So we here added 3% of cerium. It start making nucleation and make these nanoparticles inside gallium. Here we sonicated gallium to be able to observe 2 very small droplets of gallium. We saw nanoparticles of cerium produced. They're very interestingly, some of them go and attach themselves to the cerium oxide that when the competition is formed on the surface of this gallium droplets. Another information from the past that we had is that cerium and cerium oxide are known catalyst materials for breaking down CO2. Can we use it for effective reduction of CO2, this greenhouse gas. So what we did it electrochemically. We put everything, connected it to the surface. Oxide which is formed on the surface is reduced oxide of cerium. When we apply the voltage, CO2 comes to the surface, produce cerium, highly stoichiometric cerium oxide, and when we apply the voltage and reduce the surface, it goes back to cerium, reduced cerium oxide on the surface. Gallium, this graphitic material which are formed on the surface don't stick to the surface because in general the adhesive force to the surface is much lower and they can self-exfoliate. In time, the current doesn't go down. So basically the surface of this liquid metal with cerium on the surface doesn't get choked, and this reaction can continue forever. Catalytic efficiency of a reaction is about 80%, and this is the first successful conversion of CO2 into graphitic material, rather than only looking at byproduct of something like liquid or gaseous form. We can have byproduct of solid form and still run the whole system effectively forever. So it introduces very interesting prospect to the future of CO2 conversion. And phase separation. This is the last part of my talk. Now, everything that I talked to you about was about liquid metal, surface of liquid metal. And when we have something around this liquid metal in liquid form, what if we go back a little bit to the normal conventions and solidify things that we create out of liquid metals in liquid form and see whether we can use them for a different application. Here, catalytic application. We know that bismuth and tin are good catalytic material for electrochemical conversion of, for instance, CO2. What if they mix them together at under 300 degrees? We make different alloys of bismuth and tin, and then sonicate them, make smaller particles, because for catalysis we need large surface to volume ratio. And then solidify them by cooling it down, either use it in a metallic form at the core, and the surface of course is an oxide, or anneal them and produce the oxide. Use them as photocatalysts, so we can use them as electrocatalysts or photocatalysts. Now, something which is very important is bismuth melting point is 270 degrees. Tin melting point is 230. The eutectic alloy of bismuth and tin is 139 degrees melting point. Then we have 57% bismuth and the rest tin. Now, we tried different combinations of these two. Of course, melting point is less than either of bismuth and tin. Okay, we made some larger particles and we snapped them to see what happens after solidification. It's basically famous conventional metallurgy. Oh, sorry. So when we have 20% bismuth, 80% tin, we have these rods of bismuth into the ocean of crystal of tin formed, as you see. This is very similar to conventional metallurgy. When we have 80% bismuth, 20% tin, when we cool them down, they separate themselves into plates like this, into planes, crisscrossing each other. Fantastic structure. We have to look at topological insulation of these properties later. It's another, again, discussion. Then we cool them down. When it's in eutectic system, that means the solidification happens at lower temperature. They have more time to stay chaotically together. So when they cool into solid form, they don't make perfect crystal. They make these amorphous, fibrous structures together. Now, this is what is lovely for making a catalyst. If we don't sonicate them and we don't actually change the environment, the dynamic of the system, what we get on the surface is only tin oxide. But then we sonicate them. Not only get tin oxide, we get also tin dioxide and bismuth oxide on the surface. The more of this material we have, the better for catalysis generally, because it's more chaotic. Not always, but it's a rule of kind of thumb. When we sonicate everything in eutectic form, we get smaller grains as well as lots of defects. We have lots of line surface defects and edge location and increased boundaries. What does it mean? That means when we obtain the materials at eutectic form, then we did the electrochemical reduction of CO2 into forming. Here is changing back to that liquid form. Forming is liquid, and it's a liquid fuel. At only 1.1 volt, we could get the Faraday efficiency of 78%. It was almost always the highest, the best efficiency when we use a eutectic form and made the crystals out of this eutectic form. So definitely these chaotic structures having more boundaries helped a lot. Another possibility, which is my last slide, is to make photocatalyst. This is just a cute example. It's not bismuth and tin only, it's bismuth, tin, and indium added as well to make a fused metal. Fused metal melting point temperature is 62 degrees, and it's used for devices that detect heat to turn on the water showers in your room and water sprays in the room in case of a fire hazard. Anyway, going back to this, if you add silver, if you don't add silver, you can make really interesting structures. And if we anneal them, eventually we obtain annealed structure with different stoichiometry of this material, different combination of this material. And what is very important then is by mixing, combining, like cooking these things together, we can make them less or more selective to a specific pollutant that you want to attack with this photocatalyst. For instance, we show two examples of Congo red degradation, methylene blue degradation. Make them more or less selective by adding one or two of these components out or in of this system as a photocatalyst system. That was the last example. What I wanted to present was the power of these liquid metals. And I, as I said, limited myself to 4 general applications of nanoparticles in liquid form. When nanoparticles go to crystal form and in solidified into the liquid metal or solidified as a whole, heterostructuring and extracting the 2-dimensional from the surface was phase separation. As I said, conventional metallurgy, but bring that into nano submicron structures and using them. There are many other things that you can do. You can use your imagination and create new entities and find new applications out of these liquid metals. I highly suggest you to explore this. It's very easy and with minimal kind of access to characterization equipment, you can achieve a lot. Again, I have to thank the past and present member of my group and also international collaborators, especially Professor Rick Kainer and Michael Dickey, and of course, providers of fund, fleet, laureate fellowship, and the 2 universities. And more than that, I would like to thank you today to be present at this talk. And it's always happy. I feel always happy to present things. I avoided for several months, but then now that I feel that it was something that was missing a lot. Thank you very much for being here. And again, thanks Sydney Nano for allowing me to have this presentation.
Thank you very much, Kourosh. That was a great talk on the emergence of liquid metals in a lot of fields, actually, very simple fabrication, and I congratulate you for all the achievements there. So I have a few questions myself, but I open it for questions. If you have any question, you can raise your hand using the feature in Zoom, or just write your question. So you can unmute or mute if as you wish. Yep, the first question. Stefano?
Yeah, hi,
Yep,
Amin.
go ahead.
Thanks for the presentation, very interesting. So I have a question about the ITO that you were making. So I was wondering if you are able to fill up a nano gap that is something around few nanometers in width and 200 nanometer tall with an homogeneous ITO layer. Instead of having a two-dimensional structure, it's filling up a nano gap. Because I thought that the liquid metal could be a very nice way of doing it. But
it's possible to use the process and make different structures, not only in two-dimensional, also in three-dimensional. Saying that, then again, you need to use sacrificial layers to do these things. Again, whether you can use the liquid metal itself as a sacrificial layer or add something to the liquid metal to give you that possibility, again, that's something that has to be explored.
mm-hmm. Okay.
So I hope that I answered your question.
I mean, yeah, so maybe we can discuss this
Yeah, sure.
in the future.
Please feel free to contact me anytime. That would be great. I think it's an interesting idea.
Okay, thank you.
Okay, next, is there anyone? Okay, if not, I asked my question. So the application and the simple fabrication are actually really broad. You mentioned something about consumer electronics like display, transistors. Like, could we think about expanding it to biomedical application? Are you exploring those? I know, for example, I mean, on another topic, I mean, you didn't mention your great work on gastroenterology.
Yeah.
And the pH sensor was really a big initiative with the company Atmo Bioscience now in work. But I mean, just for the liquid metals application in biomedical, do you think any pathway would exist for them?
Look, that's a very interesting question. We started looking at the bio application more seriously these days. I can tell you, gallium traditionally and gallium nitride and compounds of gallium are known to have impact on inflammatory properties of the gut. Now, traditionally they were used as drugs and medicine. People can take this at low concentrations, and some part, very small amount is absorbed. The rest remains in the gut and leaves the body and reduce the inflammation in the gut. There are many papers, and still is used not very commonly in many places as the drug that's allowed by the government of the country. Liquid metal gallium, when you reduce the size, when you sonicate it, make it 100, 200 nanometers in size, can be swallowed, can be absorbed into epithelial cells. It can be lung or it can be gut, right? And it changes the properties of epithelial cells. It can be absorbed into macrophages and change the behavior of the macrophages. It changed the way that they produce enzymes, cytokines. Mentioning those, for instance, we are talking about we have problems at the moment with the virus. Actually, they can play a big role as suppressant of bacteria, suppressant of the action that shouldn't happen in this kind of cells, or improving or enhance the properties. It's fascinating. Actually, the more we are exploring it these days, the more I realize that it could be the biggest thing that the medical community and the basically investigators have forgotten to go back to and look at. Yeah, sky's the limit, and we are doing some part of it. But I think it's that the field is expanding very rapidly as well in this area. So things are happening here, and fascinating to look at and fascinating to explore.
Okay. I think one of our colleagues says I'm in a noisy place, so I'm reading the question. When flexible ITO sheets are printed, is there a sacrifice in sheet resistance compared to existing ones?
Look, our ITO 2 layers, they were very close, the conductivity, to kind of bad quality ITO, commercial ITOs that you buy in the market, not the very good quality one. The good quality ones, they have conductivity of an order of magnitude better than ours. But it doesn't mean that our conductivity was bad, because we only deposit 2 layers. So for 3 layers we tried. The reason we couldn't achieve the 3 layers at the time was we were doing this by hand. And you can imagine your hand shakes anytime you want to put the 3rd layer. If you're lucky, you can make the 2nd layer. Generally, the 3rd layer, we could never become lucky. Now, we purchased very specific machine that goes up and down by a resolution of, spatially by a resolution of 1 nanometer. And this machine can go down, put the 2nd layer, and go up. So we eliminated the bad effect of hand in the fabrication of and placement of the layers. Now we can go to 3 layers or 4 layers. Now our conductivity is better than any other commercial system in the market.
Wow.
But we haven't reported that yet.
Yeah. Okay. So another question, which is basically a comment for me. It says, could we get the slides? I know we get we are recording this session, but if we can get the slides of the presentation, would be good. I will ask Kourosh later. Now, Ali, I think you go ahead.
Thanks. Thanks, Professor Kalantar-Zadeh. It was a really interesting presentation. Sorry, because I may not understand this field because it's not my field. I'm coming from civil engineering, but they look quite interesting. And I was wondering what would be the application of these types of technologies in possibly construction and civil engineering?
Look, that's a very important question. So, do you remember I talked about conversion of CO2, right?
Yes, yeah.
And then producing a carbonaceous material, 2-dimensional carbonaceous material. Now, imagine you want to extract the CO2 out of air, right? And you produce lots of carbon. What do you do with these carbon sheets? So I used to tell everyone, hey, we just dig a hole, put it back in the ground, or burn it again, right, and produce more CO2, and then we convert it again, like producing coal and converting back coal to, and use it again. But when I was talking to one of the investors, he told us, hey, this carbonaceous material is the best material for making construction elements from it. So it's carbon, it's super light, you can squeeze them together, make them very hard structurally, and use them in making, instead of using bricks, you have bricks made of carbon. I don't know. It would be burnt or not is another question about safety. But yeah, you see that many, for instance, things these days, or airplane materials, are made of carbon fibers. So imagine you make carbon fibers out of this. Super cheap, because we're talking about megatons, gigatons of carbon in the air that has to be converted back to carbon dioxide, that has to be converted back to carbon, and use all those materials. You don't want to make piles of carbon when you do the conversion, right? You want to use them somewhere. It seems that construction is the best area to use them.
Thanks very much. I think one of the applications could be in concrete.
Yeah,
it is one of the biggest producers of carbon dioxide.
You're quite correct, replacing concrete.
Thanks very much.
No problem.
Fantastic. So I think we have time for the last question, Anusha.
Hi, thank you very much for the wonderful presentation. Sorry, I was in a noisy place just now. I have another question, also again ITO, and it's very interesting. Did you say that this was made without any machine? So do you mean that we can use this technique, fabrication technique, in like without advanced fabrication environment? That would be really cool. And also I was wondering what kind of substrate we can do this printing on. I see that you've done it on like a PET or some substrate. Can we do it on PDMS and other like silicone substrates as well? Thank you.
Okay, so there was no limit for using the substrate, and it's the big advantage of this. For instance, when you do chemical vapor deposition, when you use sputtering, nucleation happen on the substrate. Substrate has a very big impact on this nucleation. Here, the only, almost one and only limitation is the melting point of the substrate. You remember we said that they melt at around 200 degrees. So we can use Kapton, that the melting point is much higher than that if you're looking at something flexible. But if the melting point of the polymer that you want to transfer this to with the direct method is less than 200 degrees, then of course you destroy the substrate. It's possible to have a transfer from a secondary substrate to the very to any substrate that you want to transfer it to. Then it increases the cost. But if you want to have a direct transfer, the substrate should tolerate 200-degree temperature.
Okay, fantastic. I can see one more question there, but do you have, Kourosh, do you have time
Yeah,
to have this question answered? So, yep, that's fine. Roy, please go ahead. Hello, Roy.
Perhaps
Hi,
the
Roy.
microphone is disconnected.
Hello.
Yeah, go ahead, please.
You can hear me?
Yeah.
Okay. Yes, I mean, sorry, two quick questions, but perhaps two long answers for the time you have. I'm not a specialist in your field. I work a lot now with space policy, with the space agency. And I'm wondering whether your work has perhaps longer term implications, the liquid metal work. And you mentioned the porous materials used for battery and power, which could of course be extremely important in anything small scale has had to be incorporated in rocketry and in aerospace applications, even in applications that might be undertaken on the moon when we get there.
Yeah.
Now, are you already thinking that far ahead, so to speak? The aerospace industry would be interested, I suppose, in the applications of this. And the second, again, a very remote question for you. One of the key questions affecting Australian geopolitics in relation to the States is the question of what to do with the rare earths, particularly of their separation. And the separation of the rare earths that are, of course, essential to iPhones and other commodities that we have are really very important, since we are so dependent upon China in this respect. And it's the separation technology that is holding us back.
Yeah, correct.
Now, are you at all in a position, or is your team in a position to think about that? Because it could be transformative, if you were.
Okay, so answering your first question, perhaps I sort of answered them partly. I said we can make very porous material, and your question was about that one. The biggest kind of advancement should be when the electrolyte suitable for that cavern and also the fillers for these porous materials are made. So now we have, what we created is the most porous carbon, called this holy carbon, really. But I'm not a person who makes batteries, so the next step should be done by other investigators. Or when we talk about very light structures, these are the structures can be used in aerospace or aviation industries. At low cost, and may be able to transform those industries as well in the future. Then again, it's an imagination at the moment. Now, about the extraction. Actually, it's a very interesting question. Gallium itself is not a cheap material. It's about $200 per kilogram. But gallium is very abundant. It's because extraction of gallium is costly. Now, this is why all these extractions and processes are done in China, because it's cheaper there, and they sell it back to us. They just take the mining materials from us and they extract them, selling them back to us and to America. Indium is not that, of course, abundant. It's not abundant at all. But it's possible to actually use these materials for extraction. As you know, mercury is used extensively in mines, and that's the biggest problems with gold mines, platinum mines, the use of mercury, the pollution that comes out of this. Can we use mercury? Can we use gallium, which doesn't produce that kind of pollution to the environment, and it's not hazardous for living creatures? We should look at it. I already talked to some of the companies. I cannot name them because this is going to be recorded and put online. But look, all these possibilities should be explored, and I think it's possible. I think they were very good questions. They need investment, and I'm sure there will be very good return investment for those investments.
Fantastic. Thank you. Thank you on the note on geopolitical aspects of nanotechnology. So I think we thank Kourosh.
Thank you very much
for this great presentation. And I thank you everyone for joining today. And again, a virtual clap. Unfortunately, we can't have it face to face, but thank you very much and goodbye, everybody.
Thank you.
Thank you. Bye-bye.
Bye.